So welcome to the video. Today we are going to take a look at how to do a paired t-test on version 31 of SPSS. So we're going to use this test when we have an independent categorical variable comprised of two levels. So that's a within participants or within subjects categorical variable. So that's typically 2 time points. And when we have a continuous dependent variable. So for this example, we are going to imagine that these numbers here are percentages and they represent the extent to which patients adhere to treatments that they are receiving. So for example, if they're told to take pills, do they take those pills? And we are looking at whether level of adherence differs before and after receiving education about the value of those treatments. So the t-test is going to tell us, is there a significant difference in patient adherence to medication or treatment before education compared to after education? So let's take a look at how to put these data into SPSS. So we're going to go down to variable view. So we're actually already in variable view, and then we'll go to this name column and let's put before here. So before represents before education, and then let's put after here. So that represents after education. And then we're just going to use this measures column here to indicate that we have scale data, which is basically another way of saying that we have continuous data. Then we can go to data view and we can see that we have before and after now at the top of these two columns. And if we go to our spreadsheet, we can select all of the data by selecting that top left cell, scrolling down, and then while holding shift, selecting the bottom right cell, and then going to Command or Control C, and then going back to SPSS and selecting the top left cell. Then we can go to Command or Control V to paste those data in. If that doesn't work, which is sometimes the case, we can go up to Edit and then down to Paste, and that will put those data in. So one of the assumptions of this test is that the differences between these two variables are normally distributed. So to check this assumption, we actually have to create an additional variable, and we can do this by going up to Transform and then down to Compute Variable. And then we can transfer before over here using this arrow. Then we can put this minus symbol here. So we click on that. And then we transfer this after variable over here. And then we can give a name to our new variable or column. So let's call that difference. Then we'll go to OK, and that's going to create this new variable for us. So here, for example, we can see that we have a value of 53 before education, and we have a value of 63 after education. So if we minus 63 from 53, we get a value of minus 10, and then we just have the same thing all throughout that column. So now we can perform a normality test to determine whether the values in this column are normally distributed. And to do this, we can go to Analyze, then to Descriptive Statistics, then across to Explore. Then we can transfer this difference variable to the dependent list, and we can go to Plots, and we can untick stem and leaf. We can tick histogram, we can tick normality plots of tests, then we can go to continue, and then we can go to OK. And then we can take a look at this tests of normality table, and this actually has two normality tests within it. So it has the Shapiro-Wilk test on the right, and it has the Kolmogorov-Smirnov test on the left. And typically we use this test on the left when we have more than 50 rows or participants, and we typically use this test on the right when we have fewer than 50 rows or participants. So in this case, we actually have 30 participants. So we're going to focus on the Shapiro-Wilk test, and specifically we're going to look at this sig column, and we want to see that the value here is above 0.05. So here we have a value of 0.158. Obviously this is above 0.05, and that suggests that the data are normally distributed. As well as this table, you can look at this histogram as well that we've generated. And what you want to see in a histogram when you're assessing whether your data are normally distributed is that you have a symmetrical bell-shaped distribution. This somewhat corresponds to that, but it's not especially convincing. Normally, I prefer to stick to these normality tests when determining whether the data are normally distributed, because they provide you with a more objective answer, i.e. is this value above or below 0.05, whereas if you're looking at the histograms, it's a bit more subjective. And if you find that your data are not normally distributed, you might consider doing a Wilcoxon signed ranked test instead of the paired t-test, as it's the non-parametric equivalent and it doesn't make this assumption about normality. So in this case, we are going to say that the data are normally distributed, and we will continue with the paired t-test. So to do this, we can go up to Analyze, then we can go down to Compare Means and Proportions, and then we can go over to Paired Samples t-test, and then we can just transfer before and after over here using this arrow, and then we can go to OK to run the analysis. And we can start off by looking at these paired sample statistics. Specifically, let's look at this mean column here, and we can see that before we have a mean of about 59, so that's the level of adherence before education, and after we have a slightly higher level of adherence to treatment, represented by this value of about 68. So we can see that adherence was better after education compared to before, but we don't yet know whether that difference was significant. So to determine this, we can go to this paired samples test table, and we can look at this significance part of it. And we actually have two p-values that we can consider here. So whether you consider this one here or this one here depends on whether you had a one-sided directional hypothesis versus a two-sided non-directional hypothesis. So the former, a one-sided directional hypothesis, in this case would be something like it was hypothesized that levels of adherence would be significantly greater after the intervention compared to before. So you're predicting which time points would have the higher or lower value. Whereas a two-sided or non-directional hypothesis would be something like it was predicted that there would be a significant difference between the two time points in terms of adherence. So it's less specific than the one-sided hypothesis. So let's imagine that we had a one-sided hypothesis. So we can look at this value here, which is less than 0.001. And as this is less than 0.05, it indicates that there was a significant difference between before and after education with respect to the level of adherence to treatment. So that's essentially how we interpret the results of the paired t-test, but let's now take a look at how we can report these results. So I have this example here, and I've started off by saying that a paired t-test was conducted to compare adherence before and after the intervention, and then I've said that a Shapiro-Wilk test indicated that the differences between the time points were normally distributed, and then I've inserted the statistics here. So we have a W value of 0.95, and if we go back to the output and scroll up towards the top, we have this test of normality table, and we have this statistic column here in the Shapiro-Wilk half of the table, and we've just rounded this value here to 2 decimal places, so 0.95, and we have a degrees of freedom value of 30 and a p or sig value of 0.158. So that's what we have here. We have the degrees of freedom value here in brackets, and then we have this p-value here of 0.158. And then we've said that adherence was significantly lower before the intervention compared to after, and we've inserted some means and standard deviations. So we have a mean level of adherence before the intervention of 59.50. And if we scroll back down in the outputs, we can see that that is coming from this paired sample statistics table and from this before row where the mean is 59.50, and we have a standard deviation of 11.14, which is what we have here. And then we've just reported the mean and standard deviation for after education, which is just getting from here and from here. Next, we have the results of the t-test itself. So we've said that t equals negative 12.48, and we're getting that from the paired samples test table and from the t column, where we've rounded this value here to 2 decimal places. We also have a degrees of freedom value of 29 and a p-value of less than 0.001. And here's the degrees of freedom in the results section, and here is the p-value of less than 0.001. Finally, we have this effect size was large sentence, and we said that Cohen's D was negative 2.28, and we're getting that from this paired samples effect sizes table and from the Cohen's D row and the point estimate column, where we've rounded this value here to 2 decimal places. And we've described that value as large based on these criteria here. So values between 0 and 0.2 are typically considered very small. Those between 0.2 and 0.5 are typically considered small. Those between 0.5 and 0.8 represent medium effects, and those above 0.8 represent large effects. And as described here, those same thresholds apply when we have negative values. So here we have a negative value of 2.28, and as this is further from 0 than 0.8, we've described this as a large effect. So that's basically it for the paired samples t-test on version 31 of SPSS. If you have any questions, just let me know in a comment and I'll try to get back to you. Thank you very much for watching, and I'll see you next time.